Okay, I suggest to start. So welcome everyone. And today we are pleased to have Sasha Zhiboedov, who will talk about event shapes and light ray operators, their OPE and superconvergence. So please start.
Well, thanks very much for the invitation. It's a great pleasure to be back in Moscow, at least virtually. I will talk about some work which has been doing actually for a while already, but there was some interesting developments recently. It is based on papers written with this gentleman and this lady, and please interrupt me and ask questions. I hope it will be self-contained and understandable. Okay, let's start. So let's consider, just to set the stage, annihilation of electron-positron pair into hadrons. So we create a virtual photon that couples to electromagnetic current, and then through complicated QCD dynamics, we produce some finite state, which you measure in some colorimeters, some detectors. And one question we can ask is that given a total energy, total scattering energy in the state, so this little q, momentum little q, how is it divided in the final state? And this question, it's of course depends on the dynamics, how if we produce jets or we do not produce jets. And one way we can try to understand the dynamic is to try to characterize these fluxes of energy at infinity. So this would be our question for the stock. And in QCD, the final state is usually described by what is known infrared and collinear safe observables or event shapes. Energy correlations, thrust, C parameter doesn't matter. But for the stock, I will address this question in the framework of conformal field theories. So conformal field theories, they do not have a dimensionful scale. And I will try to convince you that even though these theories are conformal, still the energy fluxes that you produce are very non-trivial. And on the way, we can learn many things which can be useful for QCD. And one of the exciting aspects of this problem actually is that in the last couple of years, people in QCD were also actively studying these observables, and there is an interesting interplay at the moment between these formal developments and real actual QCD computations that could be measured. So I will mention that. So yeah, the main player is this energy correlator, which I would like to discuss. And this is defined as follows formally, or this is how it's defined in the textbooks. So let's say you have some state created by operator acting on the vacuum. In the usual experiments, it's electromagnetic current acting on the vacuum. It evolves, and then we consider a complete set of final states. We measure energy fluxes of particles into colorimeters. The probability measures given by differential cross-section, and we can measure these things. This was introduced in say 78 in this paper. And this observable in the context of a plus, a minus, it's very well measured. There is a precise experimental data. And on the theory side, the situation is the following. The first leading correction was computed in 1978. And then for a long time, there was no, it was computed numerically first, the next correction. But analytically, the next correction was computed 40 years later in 2018. And somehow, starting from this paper, there has been a lot of activity in trying to understand these observables. Already at the next order, so next to next leading order, it's known numerically. It was computed in 2017. And as you might be familiar, say if you're dealing with amplitudes which involve massless particles, the scattering amplitudes are themselves infrared divergent. But here, because the observable is physical, all the infrared divergences cancel, but this cancellation is delicate. So this is one way, of course, to measure, to characterize the final state. And you can ask, well, what is special about energy correlators? And something special is, I think it was first realized by Sveshnikov and Tkachov here in Moscow in '95, is that the previous definition, which I gave you in terms of scattering amplitudes and cross sections, it can be restated in terms of matrix elements of local operators. So like in quantum mechanics, we have a state psi, which is created by operator O. And so we have O and O dagger. And as our detectors, like in quantum mechanics, we insert also some Hermitian operators. And here, these operators are stress tensors, which are inserted at infinity or at the position of detector, and they integrated over time. This is just a running time of the experiment. And the claim is that if you consider a theory which is free in the IR, so it's just a set of free particles, and you act with these operators on the final states, you recover, they act in a simple way. They simply measure the energy flux in a given direction. So in other words, this definition precisely reproduces this one if you insert a complete set of states as usual. And actually, this is something which was discussed recently, as I said, also people thinking how to characterize just structure. You can think of probably all, or maybe almost all observables which are studied in QCD in two ways. Sort of, there are two types of observables. One is called so-called weighted cross sections. Weighted cross sections, exactly energy correlator-like observable, where there is some distribution of energy, and we measure it. And there are other observables which are different from these ones, but even these observables, their moments are related to energy correlators. In other words, this seems to be a very universal set of observables which you can use to characterize your events, and they're widely used. Now let me state a little bit the space-time picture of what are we talking about. Well, the space-time picture is that the following. Since I consider massless particles, it's a conformal field theory, there is no scale. So massless particles, they propagate to null infinity. So this is a Penrose diagram of Minkowski space. Here it's evaporating black hole, but it doesn't matter. It's the particles reach to null infinity, and detectors are integrated along the null infinity and measure the energy. And since it's a conformal field theory, there is nothing special about infinity or null infinity. You can start with Minkowski space, map it to a cylinder, which is R times S3. So you will have the so-called Poincare patch. And then you can continue correlators everywhere. And because in conformal theory, you have inversions, infinity, and the origin fundamental are the same. And if you do this conformal transformation and you map this infinity to some finite space, you see that these detectors are nothing but light ray operators. So what is a light ray operator? You take a local operator, stress tensor, and you integrate it along the null ray. So this is a usual light coordinates UV and transverse coordinate Y. These are very special operators in quantum field theory, because as you know, in a quantum field theory, the local energy is not bounded from below. But these operators are. This has been proven recently, so this is a nice operators. And so more generally for my talks, then, as I told you, there is a target O and O dagger, and there are these calorimeters, and calorimeters are light ray operators. So from the conformal field theory point of view, event shapes are matrix elements of light ray operators. So that's what I will be talking about: matrix elements of light ray operators. Now,
sorry, can I ask one thing?
Yes,
on
please.
the previous slide, you had N on the left and V and Y on the right.
Yes.
The same?
Thank you. So this N and Y are related by stereographic projection. So you imagine a sphere, it's defined by N, you project on a plane, and you get a Y. So,
okay, so Y labels the coordinate on like Scri plus, right?
Yes, you can think about that, but yeah, you can introduce a set of coordinates which relate a sphere to the plane, and the Y will be just a stereographic projection.
And then V is the coordinate along the null.
Yeah, is this integral along this blue curve. So you have this time. You turn on the detector, say at spatial infinity, you detect the radiation, and you turn it off at infinity. And so this V is a time along which you integrate along Scri.
So it's just like one-dimensional line. It's not
one-dimensional line. Yeah, one-dimensional line. Yeah.
Oh, okay, thank you.
Okay, so from the theoretical point of view, also let me mention, because it may be interesting for some of you, is that, as I tried to explain already, is that this event shapes, they're interesting objects. They live somewhat in between scattering amplitudes and correlation functions. They're in between because if you have amplitudes, you can square them, compute weighted cross sections, and get the event shape. On the other hand, if you have a correlator, you can also do something with it, and you get this event shape. But the set of tools which people use in theoretical analysis of both objects is quite different, because there is an interesting interplay here, and also some context in which this light ray operators recently were discussed in the literature is that one is they appear in the discussions of so-called analyticity and spin, which is a fundamental property of quantum field theory, or the fact that operator lives on rigid trajectories. Then in the context of event shapes, as I just described, but also I will mention today, if you do ADS CFT, it's related to the physics of gravitational shocks. Gravitational shock being a gravitational field of a relativistic particle. And also they appear in quantum information theory approaches to quantum field theory, where you study some modular Hamiltonians, modular flows, and so they're very common objects in different contexts. The plan of my talk includes 3 parts. So I want to first tell you what is a picture of event shapes in N=4 super young Mills, which would be sort of reminiscent of QCD, and what is known about it. Then I would like, and this part is perturbative. We can do perturbation theory at weak coupling, perturbation theory at strong coupling, and see what we get. Then the second part, I will tell you about light ray OPE. This is a non-perturbative tool, so we go from perturbative to non-perturbative here. And finally, if I have time, I will comment on superconvergence. Superconvergence is it's a set of sum rules. It's a sum rules and gravitational theories, which also has been actively recently discussed, and they're interesting for some reason. So I will try to discuss that. Any questions at this point? Okay. Please interrupt me if you have questions. Event shapes in N=4. So here, let me consider the stress energy supermultiplet. So it includes stress tensor, which is a conserved current. It includes spin 1 current, which is a generator of R symmetry, and it includes this scalars and some representation 20 prime of R symmetry, but it doesn't really matter much. And what will matter much is that, as I explained, say if you want to study 2-point energy correlator, you need a 4-point function, in and out state for the target and 2 detectors. And if you say care about energy flux in a state created by a current, conserved current, there is a supersymmetry word identity which relates it to the scalar. And in conformal field theory, the 4-point function of scalar primaries by symmetries is fixed up to a function of cross ratios. So therefore, I will sweep it under the rug. So you can think in mind about measuring energy in some state created by current, but technically it all reduces through word identities to just studying a scalar 4-point functions and doing something with it. And this function, which encodes dynamics of the theory, it's known up to 3 loops in planar limit at weak coupling, integron up to 7 loops, and I think, if I'm not mistaken, strong coupling, it's known via ADS CFT correspondence. So what do you do? Just in practice, let me state precisely what is the goal. If you want to compute this energy correlator, you start with a 4-point function, which is something you have to compute. So you can compute it in Euclidean space, whatever you use, Feynman diagrams or whatever you prefer. Then you have to continue to Minkowski space, and the operators here are ordered as written. It's not the ordered product. It's really a Whiteman function. After you got the Whiteman function, you integrate over detector times. So you insert this detectors at infinity and you integrate over time. And finally, you do the Fourier transform if you want your target or your initial state to carry a certain energy. There is some technical tools to do that. It's easy to do in Mellon space. It doesn't matter so much. but you can do that. And in this way, at every step, your quantity is manifestly infrared finite. You do not have to do the phase space integrals and find sum over final states. In QCD, this is complicated. Say there was this paper this year, and it's complicated than the standard technique. However, in C conformal field theories, it is very powerful, and then we will learn some lessons which we can transform to QCD. If you want to compute it in a conventional way, so using amplitudes, and I want to say it because I think there was a lot of papers relevant for this written by Moscow group. As I said already, you compute first a form factor, which is a scattering transition between a state created by operator into some final states. You take a square, you integrate over phase space, and you average with energies. And here, because all these form factors are infrared divergent, so you have to introduce infrared regulator, and then again, according to the classical theorems, the divergences cancel, etc., etc. This you can do in perturbation theory, when emitting one gluon costs you a power of coupling, and then if you work order by order in G Young-Mills, you have a cancellation between usual real and virtual singularities. And these form factors are very rich mathematically. There is a lot of structure which was recently studied in amplitude community, and it was studied a lot by, say, the Moscow group and the group, the English group. However, if you go, say, to strong coupling, where the form factor is given by area in ADS, emission of particles is not suppressed. So you cannot just cancel infrared divergences summing a finite number of particles like you can do at weak coupling. However, you can still use the correlation functions. And so this is an example how you can use the amplitudes at weak coupling, but at finite coupling, this picture with particles is a perturbative one, and we will use correlation functions. Now, let me just tell you what is known about this observable. Let me introduce an angle between detectors chi, and this zeta is 1 minus cos chi over 2, so it goes between 0 and 1. Yeah.
Maybe before you proceed, what is the relation to Wilson loop with cusps? Can you
yes
with insertion of operators, or
I think so. Say at least here, so the form factor at strong coupling, this picture here, it's a Wilson line.
Mm-hmm.
It has all these particles, but it's not closed, it's periodic. So in ADS, you consider a periodic Wilson line with a period given by the momentum of the operator. So and then the form factor is given by the area. I believe there were papers recently, maybe by Amit Sever and collaborators, where they studied the structure at weak coupling as well, and so I think there is a way to think about this even at weak coupling as Wilson lines, but they're not closed as for scattering amplitudes, but periodic, but still integrability and many things they do apply.
Okay, but then you square it, sort of effectively it becomes closed.
Yes, then you square it, and so this operation of summing over all states, because here you have to sum over all states and square it and integrating over phase space, I don't have a nice interpretation. This, from the point of view of Wilson line, it does not look particularly natural.
Okay, thank you.
Yes, let's look at this observable at weak coupling. At one loop or leading order, it's just a log. Now, and this is the same, if you go to QCD, you get the same log, but with some polynomial, which is more complicated. You get to next to leading order, it gets more complicated. You start getting this logarithms and polylogarithms. It's not, some of you might be familiar that it's common to introduce a weight of functions, say weight of zeta function at value n is n, weight of a log is 1, weight of pi is 1, weight of Li2 is 2. And so this is not a homogeneous function. So you can see here Li3, but also you can see here a log square. So this is weight 3 and this is weight 2. Nevertheless, again, in QCD, you get the same sort of what's called alphabet. So you get the same basis of functions but with more complicated polynomials. And as far as I know, also that this was useful to have this first in n equals 4. Finally, last year, we computed it to next leading order, something which is not known in QCD, and there you get harmonic polylogarithms and elliptic integrals. So the prediction would be that if someone dares to compute it in QCD, they will have to also deal with this elliptic integrals. And but I think the basis will be the same, the basis of integrals. Finally, at strong coupling, there is this famous result of Hoffman-Maldacena, where the energy correlator goes to a constant plus small ripples suppressed by 1/2 coupling. So what is the physical picture? We can based on this, we can draw a qualitative physical picture of what's happening. And let me consider, say, tooth coupling equals 0.1. Then you have this energy shape, which is peaked in forward limit and in a backward limit. And this is nothing but the signature of jets. What jet is a collimated flux of energy. So your observable is peaked at when you put two detectors forward or backward. And then as you increase coupling, say, if I use a supergravity result, you see the curve flattens. So this is the famous result that as you increase the coupling, the jets disappear. So there are no jets at strong coupling in n equals 4. At weak coupling, this curve looks identical to QCD. It's also very similar. Yeah, there is also this relation, which is if you consider...
Excuse me, Sasha.
Yes.
You also expect 3 jet events, 4 jet events. Where are they?
Yes, so to probe those, you have to consider more detectors. Because if you have 3 jet event, but you have only 2 detectors, you effectively integrate over all other events. So if you want to resolve 3-4 jet events with these observables, you have to put more detectors. So if we consider 3 detectors at strong coupling, you again get a constant. But at weak coupling, you will get the 3 jet peak. So that's a picture. So you will not see this because, in other words, this observables is too crude to see those.
Wait a second. If you have 3 jets, then you have correlation between the first one and the second. I mean, 2 of them, right? And these are not back to back, right?
Yes. So
they would probably have some, contribution to the correlator, right?
Yes. They will contribute, say, here, for example. So here, if you put 2 detectors at some random angle, and you have 3 jets where you have 2 jets and 2 detectors and a third one, this will contribute to this observable. But you don't see this peak like you see at small angles and at large angles. But it does contribute, yes. 3 jet events, they do contribute at intermediate angles or whatever angles.
Okay, so the picture must be quite different at leading order and next to leading order. It doesn't seem so. In the central part, in the part where, not back to back.
Yes.
Next to leading order should be quite different because of this is 3 jets basically. And there is not so much of a difference in this picture in the region, not back to back region. At intermediate angle.
Yes, so I think that what happens is that even if you look at leading order result, if you look in the middle, effectively it's a 3 jet. It's already a 3 jet event because you have 2 particles and you emit a third gluon, and you emit 2 particles and the third gluon we do not detect. So let's think in the center of mass picture. So already at leading order. Here, effectively, to compute this observable, you have 3 particles in the final states, and you detect 2, and third is not detected. And so that's why you do not have this qualitative difference. I think what is true is that here I didn't draw it because it's a bit trivial, but in a sense, this leading order, it's not a leading order to really.
I see. Understand.
You will have delta functions.
It's not okay. It's not 0th order. It's
not. It's a first order. Yeah. Okay, that's right. Okay, so there is this relation to QCD, this maximal transcendentality, when you expand at small and large angles, and you have.
Sorry, excuse me. So you don't give here. I mean, you don't show the zeroth order. You don't sum up.
Yeah, I didn't show because it's a 2 delta functions. Because to zeroth order, if we think in the center of mass, to zeroth order, we just create 2 particles like this. And so
I understand, but and you don't sum up this contribution to what's shown here. Right?
Yeah, these contributions are not it's not shown. So there is a contact terms which I don't show here. The contact terms come effectively from this.
And there is no interference.
I think there is in principle there is interference, but here there is no interference between well, here, say for example, there is no leading order because the contribution here is 0. It does not contribute, so at intermediate angles it does not. I don't think there is interference, but maybe we can discuss it later, because I was going to talk about interference, but in a slightly different context. But so here, just to give a sharp, maybe sharp answer, we are computing these things, and to leading orders, this f is just 1 and given by 2 delta functions, and then to next order, you get some contributions. There is interference in a sense if we write f as a series and we take its absolute square, there is across terms.
Okay.
Okay, so let me just sum up the physical picture with a little movie. So how does this quantum state looks at 0 couplings? Well, we have jets. So at each event, say your state decays into a few, say here, 2 particles, and then either you detect them or not. And so this is what we were just discussing. This to leading order, you have 2 delta functions, which I didn't write on the previous slide. On the other hand, on strong coupling, your state looks like a blob. So actually, no matter how many detectors you put, you will just measure energy over volume of the sphere. So this is this. So the quantum state looks, that's how it changes. And intermediate coupling, we have some intermediate picture where in between these 2. Now, let me try to, let's say if I want to make this picture at intermediate couplings quantitative rather than qualitative, like here, I think here we get already a qualitative picture, right? But how do we interpolate between the 2? And this is this second part, which I want to tell you about the light ray OPE, how you can use some tools to make statements about finite coupling. Any questions before I go there?
I wanted to ask one thing. So when you say that mention jets, do you actually mean that these are multi-particle states?
Yes, at finite so what happens is that at finite coupling, you start branching out particles and you start get these collimated fluxes. So if you do order by order, we just have some fixed number of particles, but in general, what I call the jet is a collimated flux of energy. It can be any number of particles at finite coupling.
So those quantities that you presented, they like to compute them, you need like all-point correlators. Is it true?
No, you need a 4-point. You need a 4-point correlator. So yes, that's one thing. So if you want to compute them using amplitudes, then yes, you need amplitudes with arbitrary number of particles. But this occurs because you're quantum mechanically resolving the identity. So this is the definition of the operator of the object that we are studying. This measures energy flux in a given quantum state. But here there are no particles. You see, this is just some quantum state created by O, and we measure expectation values of G's in this quantum state. So there is no particles here. But if you try to introduce a complete set of states by introducing particles, then you have to sum over any number of them.
Okay, thank you. I see.
Okay. Let me then proceed to the light ray OPE. So operator product expansion, it's familiar for local operators, is a very powerful tool in a sense that it enables to formulate the bootstrap equations. So you start with two operators and you exchange it by sum over a complete set of operators with some structure constant. The structure constant conformal 3-point functions. They also, more precisely, they involve some derivatives, dependence on the distance, but this is fixed in terms of conformal symmetry. And then by imposing associativity of the operator algebra, you get bootstrap equations, which people used recently a lot to extract some mileage. Now you can ask, can we do the same for the energy colorimeters? So we have two detectors on a celestial sphere at some directions. And you can ask, maybe we can do the same. There is a distance between them on a sphere, which is an angle. And we can now take the angle to be small and try to write a formula like that. So there is a small angle expansion for the light ray operators. Is there such a formula? And the punchline is that yes, there is. And it's a quite remarkable formula. It will take quite some time for me to explain how to derive it, and I will only sketch it, but I'll try to explain what is happening here and what is the physical meaning of it. So, okay, here in the left-hand side, there is a product of two detectors. These two detectors are two light ray operators that sit at null infinity at different positions on the sphere. Now, as before in the usual OPE, we write it as a sum of light ray operators. These light ray operators, here there are many unexplained yet labels, which I will try to explain. But this set of light ray operators, first of all, we understand what it is. And second, we understand how they contribute. Like in the previous slide, if you write a conformal OPE, you have 3-point functions, et cetera, et cetera. And these differential operators, which are fixed by conformal symmetry. This is the same formula. So now let me slowly unpack every symbol in this formula so that hopefully it becomes clear what's happening. So first of all, in the left-hand side, these operators are integrated stress tensors. So let me first discuss the OPE of two stress tensors. If you consider OPE of two stress tensors, you have a set of local operators of various integer spin that appear there. As we learned recently, the structure of conformal field theory it's not a theorem, but it seems like that's a correct picture that follows from recent developments. The set of operators and their quantum numbers, like dimension of spin, is not a set of isolated integers, or sorry, isolated numbers. They live on Regge trajectories. So these Regge trajectories are Regge trajectories for operators which appears in the OPE of two stress tensors. So this is a so-called Chu-Frauchi plot. It's familiar from the 60s from the pion physics. So if you can think of delta as a mass and J as a spin. So what appears here on the right-hand side, say, if you look at this O plus I, J equals 3, J equal little j equals 0, it corresponds to a point on a certain Regge trajectory. So I will explain what this little j is. It will be a transverse spin. It's a quantum number. But you look at the OPE of two T's, you take a Regge trajectory with this quantum number, and you take a point with spin equals 3 here. So you take this point, this has quantum numbers, and then you know that this operator will appear here. That's a claim. Now, here is similar. This j equal 3, j equal 2. You look at another Regge trajectory and take a point on this Regge trajectory, and to each point on Regge trajectory, there is associated a light ray operator. So first of all, is this formula, what I tell you, this sum, the first symbol, this sum over I, it's a sum over Regge trajectories. So in the light ray OPE, we sum over Regge trajectories. Now, from each Regge trajectory, which is this line in the space J, you pick certain points. So you say you take the first Regge trajectory and you take a point j equals 3, and this light ray operator will contribute. And similar with other quantum numbers. So I will slowly unpack further. But to first approximation, The light ray OPE is given by sum of radio trajectories, where I tell you which points on radio trajectories you have to take into account. Now, first, even you can ask what is the meaning of this light ray operator? What is the symbol O? So far I only mentioned this E detector, which was an integral of a stress tensor along the null ray. So this light ray operators was introduced in this paper by Peter Kravchuk and David Simmons-Duffin in 2018. And the way you define them, well, if you have a Lagrangian theory, and then say in QCD, people just wrote explicitly the expression for light ray operators in the 80s already. But if you have a non-perturbative CFT, the way you define it is you take a pair of operators and you smear it with a particular kernel. And the kernel is designed such that it's localized along the light ray, and it has a conformal properties such that the object that you get transforms as a primary operator with the right quantum numbers. Moreover, you can argue, I will not argue that if you define this object, which is just an integral of a product of two operators against some kernel, it will have poles. And it will have poles, it's related to the poles and the scattering amplitude. If you have exchange a particle, you have a pole when energy is equal to the mass of this particle. Here it's the same. This object is such that if you exchange an operator, say a light ray operator, it will have poles. And so the light ray operators in an abstract CFT defined as a residues of this kernel. Now, sometimes, and this J here can be the one interesting aspect of this J does not have to be integer. This construction works for non-integer spin. But if you take J to be integer, then what you find is what I told you already about, that this light ray operator is nothing but the integral of a local operator. And now this plus and minus, it's a so-called signature. So if you have, say, operators of even spin, they define so-called plus radio trajectory. So 2, 4, 6, you can continue in spin from even spins, or you continue in spin from odd spins. And so this is this label plus minus signature on the light ray operator, because we are continuing in spin. So here that was this, you see all these pluses. It means you start with the radio trajectory for even spin operators, but you evaluate them at an odd point. So they're truly non-local. They're some truly non-local objects. Let me now make a little bit, maybe to go from abstract formula to something concrete. Let's go back to the observable, which I described in the first part of my talk, this energy-energy correlator. You can apply this OPE formula from the previous slide, and you get a prediction that at finite coupling, this two-point energy correlator is given by sum of radio trajectories, and each radio trajectory contributes as a known function of the angle. And this known function, it's an analog of conformal block, but it's, well, celestial block, some kind of celestial block. So as I said, sum is over radio trajectories. In practice, what you do, this P's is a so-called OPE data. This is 3-point functions, but this is a 3-point function between, say, two stress tensors and this light ray operator. So at spin equal 3. And you can check that it agrees with the results that I showed you. And this, let me not even comment about that. So in practice, for example, you take a one-loop result. You take a one-loop correlation function. You expand it in the OPE. You get the sum of radio trajectories. You take each radio trajectory, continue analytically in spin, say, up to spin equal 3, plug into the previous formula, and you get the results which I was showing you before. So first, the leading order result, you get a log. At strong coupling, you also can do it, and you reproduce the results. So this is just to say that for the same observable that I described in the first part of the talk, I give you now a non-perturbative formula, which in principle, if you can compute the OP data, you can plug into this formula and compute it. Now, let's now try to ask what happens to jets. I told you that when you go from weak coupling to strong coupling, sorry, yeah.
Sasha, in the previous formula, where the coupling enters through OPE coefficients? Where
Yes. Coupling enters through OPE coefficients. So here
you didn't write them here.
Yes, I didn't write the coupling. So here delta i's depend on the coupling and P also depends on the coupling.
Okay.
Here I didn't write, so here this is linear in lambda, so it stands in front, and here it's at infinite lambda, it's a constant.
What part of it is like specific to a theory, and what part is universal? So that like Reggie trajectories part, it's a
so this formula is completely universal. It's true in any CFT, but this so say these particular numbers, this is specific for n equals 4. So if, for example, if you want to apply this formula to a critical oven model, dual to high spin theory, these numbers will be different, but the original formulas, this formula will be the same.
And this picture with the Reggie trajectories,
it's also universal. So,
and it's the same as in Pion physics. Or...
Well, in Pion physics, we have particles. Here we have operators. So the original Chu-Frauchi plot was for the spectrum of mesons and in the experiments.
But the plot is the same.
Or... Plot is the same. It's a spin as a function of mass. Here it's a spin of a dimension of delta. Yeah.
Mm. Okay, thank you.
But the difference is that in particle physics, you have Reggie trajectories, but I don't know if there is some simple interpretation. If you go, so if you're an integer spin on the Reggie trajectory, this are mesons. But if you consider spin in between, it's just some point. What I'm saying here in conformal field theories, when the analogs of mesons are local operators, but if you're in between, this also has interpretation. These are light ray operators. So that's a difference.
Mm-hmm.
We have some ideas that at least in some gravitational theories, it's related to shocks. So there is some kind of shock wave state, but maybe I'll not go into that. Okay, so and then if you have now this finite coupling formula, you look say for the small angle behavior of two-point energy correlator. It's characterized by anomalous dimension of twist two operators.
Sorry, Sasha. I'm sorry.
Yeah.
Can you come back one slide?
Yes.
Even more. Yeah. One more. So which parts of this formula are explicitly known and which are not?
So the part of this formula is known as conformal block as an explicit function, but the anomalous dimension of operators which contribute, delta i's, this is something to be computed. So this is known for some operators, but not for all of them. And the 3-point functions are also known for some operators, but not all of them. So I would say the unknowns in this formula is p's, and at finite coupling, they are not known, all of them. And delta i's are also not known, all of them, but some of them are known, and this is my next slide. So certain, thanks to integrability, certain delta i's and certain p's we know as a function of tooth coupling at any coupling.
So when you say that you know the behavior at finite coupling, what does it mean? What do you
Yes. So let me explain what I mean. So at finite coupling, we do not have the closed formula. We don't know because we know the OPE coefficients. But let me ask a simpler question. What is the small angle behavior of the energy correlator? This is given in usual. It's given by lightest operator in the sum, because it's like you take the OPE, lightest operators dominate short distances. So here it's the same. When you go to small angles, the leading lightest operator dominate. And this leading operator is a so-called twist two Reggie trajectory, which was computed using integrability methods at any coupling. So in this particular case, you know this delta I from my previous formula as a function of coupling. And so here you see that at weak coupling, this anomalous dimensions is very small. This gamma is denoted here by gamma 2 plus minus 1, doesn't matter. It's just anomalous dimension, you know it. And it's very close to 0. So the small angle behavior is 1 over theta squared. So it's singular. It has a peak. You know, when theta is small, it's 1 over theta squared. It becomes big when gamma is small. Now, as you increase the 't Hooft coupling, here's the plot, how gamma depends on 't Hooft coupling. It becomes large. And then at some point, when this gamma is equal to 2, and this happens at 't Hooft coupling, whatever, 13 point something, you don't have the singularity anymore. So you take the small angle limit of two detectors, and there is no feature. It's regular. It becomes regular. So at this point, you can say the jet has disappeared. Remember, at weak coupling, we had these peaks, and at strong coupling, we had a plateau. And here at small angle, we can interpolate and see how this thing disappears, and we can tell you exactly when it becomes regular thanks to integrability, which can compute.
But that is just for large n. What do you know about finite n?
Finite n,
Definitely
yes,
nothing.
we don't know. No. That's actually one interesting question. So as I mentioned, that there is some work on computing form factors, but I think there are many interesting problems. For example, there is this observable was never computed at non-planar level, as far as I know. So we don't know what happens. So this formula, in principle, this formula is a finite n formula, but it gets to apply it in practice, you have to know the spectrum and etc. So it gets complicated. Yeah. So what I showed you is a planar theory, finite n. I'm not saying anything. Okay. Now let me come back to this little j. So in this formula, hopefully some things become a bit clearer at this point, but there is this quantum number j, which I haven't explained to you, so let me explain that. So j is what we call transverse spin. So imagine you have a Lorentz group and you have a tensor, which in some representation of Lorentz group, you can associate a Young diagram to this tensor. Say in 4 dimensions, it will be 2 rows. And in d dimensions, it's an integer part of d over 2. And the first row of this Young diagram that corresponds to a certain tensor, I called spin. And this little j, it's a number of boxes in the second row of the Young diagram. This is called transverse spin. So therefore, in my formula, little j simply stood for the representation of this tensors, and for the number of boxes in this second row. And if you go to celestial sphere, so I told you, I think, yes, Vijay asked me before, what is the relation between n and y? And I told you it was a stereographical projection, so it's written here explicitly. And so if you have a light operator of spin j, if you look at the celestial sphere, it just behaves as a tensor with j components. So in this formula, this j refers to this number, to spin on the celestial sphere. Now we are coming back to this last term, and to explain it, let me introduce you some paradox and then its resolution. Consider now that we live on the celestial sphere, we can insert, say, 3 detectors. And now, as usual, we can consider crossing or associativity of this light OPE in different channels between detectors. So if you expand in this channel or in that channel, the result should be the same. And intuitively, and it was done rigorously recently, that if you have some singularity in one channel, so to reproduce the singularity in the other channel, you want to build some kind of a dipole object or large spin object. So just from the fact that in OPE of 2 operators, you have some non-analytic behavior, which we expect generically true, implies immediately that in the other channel, you have to have operators of arbitrarily large spin, which is not surprising, it's just the fact. However, in the papers that we wrote last year, and which I presented at the conference, the formula that I presented was like this. You see the little j here goes from 0, 2, and 4 only. So how come is that we know that we need, for associativity of these operators, we need operators of arbitrarily large transverse spin, but what I was showing you has only a finite transverse spin. And let me comment before I tell you the resolution of this tension. What is this origin? Why is it just 0, 2, and 4? This 0, 2, and 4 comes from the fact that if you look, say, at operator product expansion of two stress tensors in the conformal field theory, and you ask what are the representations that appear in this OPE, it's just a fact of conformal symmetry is that you can only have representation with 0, 2, and 4. And so that's what we had. What we had that we have these fragile trajectories. They only have 0, 2, and 4, and we derived naturally only the terms with 0, 2, and 4. However, there was this tension between this and the picture with associativity. And the resolution which we posted a few weeks ago is that what is actually missing is so-called primary descendants. What is a primary descendant? Primary descendant is that you can take a light ray operator with, say, little j equals 4 and act on it with a very special differential operator, which takes transverse spin and raises us by n units. So the idea is that you have this new special contributions with new special conformal differential operators. Let me say a few words about conformal differential operators. So if the normal Verma module consists of primary operator and its descendants by acting with derivatives. But this is not always the case. For some special quantum numbers, it can become reducible. And the famous example is a conserved current. In this case, there is a submodule. And when we define a short representation, we mod out by this submodule by decoupling all the states. But this is just the simplest examples. There is a math literature which analyzes these conformal differential operators and classifies them, and they are known. And usually they do not play a role in physics, or if you study statistical physics, you will not see them, because usually the models which satisfy unitarity, the operators satisfy so-called unitarity bound, delta minus j larger than d minus 2. And all the special differential operators, they act on representations that violate unitarity bound. That's why they don't appear normally. However, for light ray operators, I haven't explained you that, but in a conformal world, if you do this integral of a line, it flips the quantum numbers. So if you start with delta and j, after you do this light transform, it's just a conformal operation which flips quantum numbers. Sorry, it should be 1 minus j1, 1 minus delta. But the important thing is that after doing the light transform, even in unitary theory, you end up in the world which do not satisfy unitarity bounds. Theory is unitary, but from the conformal field theory point of view, you do not satisfy unitarity bounds. And what happens is that exactly the quantum numbers of light ray operators such that you can write these differential operators, they exist. And the way the higher transverse spin operators appear on the celestial sphere is through primary descendants. And coming back to the OPE of stress tensors, I told you there are only local operators of transverse spin 0, 2, and 4. And what happens is that if you want to increase transverse spin, you go above along the trajectory. And so you start to say with j equal 5, you act with differential operator, and it turns this capital J into little j. And in this way, through these differential operators, you recover this high transverse spin contributions. So let me tell you a few words. How do you detect them in the experiment? Just to have some intuition, what is this transverse spin? So if you go back to this E plus E minus and two hadrons, you can do two things. Say, electron-positron couples to electromagnetic current, which comes with some polarization. So in this case, the target has a spin. And it's common to average over polarizations of E plus E minus pair, but also sometimes in the experimental literature, there is also averaging over the beam direction. But let's not average over the beam. Let's not average over the beam. So you have this E plus E minus along this vertical axis. And then you have angles theta and phi. and psi. And so if you rotate one detector around the other, the conjugate quantum number is given here by this blue phi. And what happens is that this phi is exactly the transverse spin. And for example, if you consider the experiments with a spinning target, like electromagnetic current, and you do not average over the beam direction, and you rotate one detector along the other, you will see this dependence on phi, like you see here, cosine phi square. So one way to detect this is to consider spinning targets. But there is another way, which is if you consider more than 2 detectors. And the very cute setup was published last week in a QCD part of the archive, where it was discussed how, imagine you want to run a double slit experiment on a collider. So in the usual double slit experiment, you have 2 paths, left and a right. But in a collider experiment, instead of a left and a right, you can imagine that you're creating, you can create a pair either by exchanging a plus helicity gluon or minus helicity gluon. And this interfere. This is a quantum superposition of states. And then what happens is the fact that perturbatively you exchange this gluon, it has spin 1, you can take a pair of detectors and rotate them around each other. And this is drawn here. So you have 1 detector, say, and 2 other detectors. And then if you measure the dependence of the energy correlator on this angle, this is a transverse spin. So this is another way. So there are 2 ways to this little j quantum number. You can measure it in 2 ways. Well, one is by studying spinning targets, and another by studying, say, 3 or higher point energy correlator. There is let me make a comment on the nature of OPE. If maybe ask me, you can ask me after the talk if you want, what is the status of this OPE? Is it the same like the usual OPE, or what's the difference? I will discuss. But let me just mention in my last 1 minute beautiful picture of what is a gravity duel of all that. So we are studying collider physics, but let's go to idea CFT and see what happens. So I told you that at strong coupling, the quantum state is a blob. It's just a blob of energy which spreads. Now, if you do the dictionary, what you find is that the energy calorimeter corresponds to a gravitational shock. And this blob here corresponds to a particle that falls into the middle of ADS. So this is the duality. When you have the spreading quantum state blob, it corresponds to a particle that falls in the middle of ADS. And then when you're measuring energy in your calorimeter, it corresponds to the fact that when you cross a gravitational shock, you experience a Shapiro time delay, something which is measured with signals sent to Mars and back. And then you can study various games. Positivity of energy is mapped to causality, Shapiro time delays, and then there is a superconvergence relations that detectors commute, et cetera, et cetera. So there are some very intuitive relation on the quantum field theory side. So the energy is positive, for example, and the fact that the result of the experiment does not on the ordering of your detectors commute. However, it leads to interesting statements about gravitational theories, that gravitational shocks commute, and the theory is causal. And if you forget about where it came from, it's actually quite not obvious, and it leads to non-trivial constraints on the gravitational theories, which I don't have time to talk about. So let me summarize. I told you about some observables and some new Lorentzian methods and conformal field theories. It involves light ray operators and event shapes. And I think it's very interesting that these techniques, at the moment, there seem to be excitement, and also in people who study QCD, and there is excitement in a very formal world of studying this object. So there are some more conceptual questions which I haven't discussed. What is the abstract space of light ray operators? How to do non-conformal field theories? What to be learned? I didn't tell you about dispersive methods in quantum gravity, but essentially familiar dispersion relations like Kramer's chronic dispersion relations very closely connected to this commutativity of detectors, if you think about it. And finally, also, I think it would be interesting, say, for conformal field theories. We know that conformal field theories describe phase transitions, but these are usually Euclidean conformal field theories. Well, there are also so-called quantum critical points, and these are Lorentzian. And it would be interesting if one can study these observables in the lab. And for, say, the lesson from our paradox and its resolution with transverse spin is that it's interesting to study this oriented event shape. It's an event shape with a spinning target and where you do not average over the beam, or multi-point event shape. And just to finish, I can show you a picture, which is a work in progress. I talked to some of the authors, where they started really, apparently for some reason, it was this energy correlators was not computed at LHC, and now they're computing them, and they already some very surprising results. Let me stop here. Thank you.
Thank you. So, are there any questions?
Can you comment on what's shown here in the last transparency?
Not too much, because but roughly what is shown here is that what these authors did is that they use some open data which they know how to use, and they simply computed energy correlator in the apparently detectors at LHC have very good angular resolution. So this horizontal axis is an angle in some units, which is not known to me, at least, so they don't divide it in talks. This is a picture taken from the talk, not from the paper. What they observed, and apparently this was a surprise, that if you look at the energy correlation functions at LHC, it's small angles. So going to the left is going to smaller angles. First, there is some plateau, and this plateau apparently one can understand from type of computations which I described to you in the talk. So you have quarks and gluons, and you compute the cross sections. But then at some angles,
large angle, which is small angle here.
Sorry, yes. So this is small angle. This is smaller angles. This is going to the left is smaller angles. And so this plateau is something people expected from computations. But then apparently what was a surprise is that when you go to even smaller angles, there is a sort of phase transition where the behavior becomes very different, and it's supposed to be related to non-perturbative physics. So here somehow you can still, one of the advantages of these observables is that you can reliably compute them in perturbation theory, but in theories like QCD, when you go to very small angles, you start getting large non-perturbative corrections. And so I don't know if this behavior is understood, but I know that, say, from Jesse Teller, who is an expert, that this behavior was a surprise. So this is some new effect which was not known.
There's smaller correlation at small angles.
Yeah. There is somehow at small angles the correlation drops significantly. I don't understand or don't know the explanation of this fact, but I guess there will be papers this year with these plots, and
there must be some cuts, right? Because you have a lot of particles going in forward direction, right?
Yeah, so here I think the picture. So let's say we have a collision along the red arrows, and then we put two detectors here, these green ones, and then we study the energy correlation as a function of the angle between the green guys. And when they're becoming too close, somehow there is this sharp transition, and there is a straight line, which supposedly is related to some really hadronic physics, which is non-perturbative. Whereas this plateau apparently agrees with perturbative computations. But, But this is more of a teaser.
Okay,
Yeah. That somehow, apparently, for some reason, this observables was not studied much, and maybe there are some surprises there.
Any other questions?
So this story about descendants, is it related to the fact that the stress tensor is conserved?
No, this is, I think, really related to this fact, which I didn't explain very well, but let me try to do it now. So imagine you take an operator and you integrate it along the line on a cylinder in conformal field theory. And you integrate it with this weight that I was writing in some reference frame. It's just, in some coordinates, it's just the integral along null ray. You can ask, if you start with an operator, which is a primary with dimension delta and j, what are the conformal properties of this object, which you get by this integral? For the claim number one, that this operation is conformally invariant. So if you start with a primary, the result will be still a primary. However, the quantum numbers of this object, if you start with an object which is delta and j, it will become 1 minus j and 1 minus delta. And you see, for j, for normal and for sort of usual operators, which j are positive integers and delta is also some number, you will get something negative, something that violates unitarity bound. And I think that that's what important somehow, that you get a dimension which is 1 minus j, which for integer j is integer, and so these integer dimensions are important. Now you might be right that that even the fact that I have 1 minus delta, which for stress tensor delta is equal to d, it is also integer. It might be important, but I think just based on the resolution, it is not necessary. So if we take, but yeah, that's a good question. It might be, yeah, I should know the answer right away, but I don't. Yeah, maybe it's special for stress tensor. So my first reaction would be that it's definitely, you can have some other situation. For example, if you have a scalar from a stress energy multiplet with dimension 2 is spin 0, you still have this transverse spins. So it's not necessarily a stress tensor, it's not. But in both of these situations, the quantum numbers are integers. But if you take some stringy modes, or if you take some operator with some dimension delta and some spin, and we do the light transforms, and we do the OPE of those, whether we can have the differential operators. This
yeah, yeah. I guess it's important that its dimension is protected. That's what you're trying to say.
Yeah. And yes, this is definitely could be answered just by looking at this set of operators, but I will need to think a little bit.
Okay, thank you.
But once you integrate it over a line, you still associate the result with some point. With which one?
Well, yes. So it's a non-local operator, but if you take the starting point x and z, z is sort of, it's a direction of which you integrate, and it encodes also a polarization, effectively a polarization of the operator, so which connects to spin. Then if you think of your operator as a primary operator inserted at point x with polarization z, it transforms like this funny representation 1 minus g, 1 minus delta. But it's a non-local operator,
so in a way it's like doing a shadow transform, but more involved.
It's, yeah, so there are a set of integral transformations in Lorentzian CFTs, which was beautifully analyzed in this paper. And the shadow transform is one of this. Light transform is another example, but there are even more. There is a floodlight transform. So there are other ways, but these are the two maybe two simple examples. Yeah. Yeah. And also, yeah. Sorry.
Okay, it was another question. So if you have something to add to this.
No, maybe you please go ahead.
So I was wondering whether there is some connection with what people now do in flat space holography. So there are many common ingredients.
Okay. Yes. So I think probably there is some connection. So, for example, these light ray operators, which I'm talking about here, these are analogs of this soft photons or soft gravitons in some sense. You can consider insertions which people like to consider in flat space holography, where what they do is that they take this, say, in flat space holography, you take a null infinity and you insert some operator which creates a particle, and you insert here a plane wave. And this is the energy of a particle.
Mm-hmm.
So this is something I'm currently looking into, but from a different motivation, because here you can ask that what I told you about this energy fluxes, it characterizes the transverse structure of the quantum state. You might ask, okay, if you have a colorimeter, you can also detect the time dependence of the arrival of the radiation. And to be sensitive to this time, you can insert this exponent here. And so from the point of view of this experiment, this will be probing a longitudinal structure of the state. So, and these observables, these are still operators which transform nicely on the conformal group. They are not primaries, but they are eigenstates of special conform. It's a little bit a funny object, because it's usually primary operators are eigenstates of K with eigenvalue 0. And these objects would be eigenstates of K of special conformal with some non-zero eigenvalue. But then you can study them, and presumably in CFTs, what people do in flat space holography is studying the correlation functions of such objects. So you put some of them at scri minus, some of them at scri plus, future past null infinity, and then you study correlation functions. So then the kinematics looks the same, but the dynamics is probably different, because, well, flat space holography, it's not clear exactly what it is. Kinematically, it's studying these observables, but dynamically, say, the set of representations that they get is very different. And so kinematically, I think the relation is clear, but if there is some deeper connection, I'm not sure.
Mm-hmm. I see.
Yeah.
Any other questions? Okay, it seems that we don't have any other questions. So let's thank Sasha for his nice talk.